let's talk about solar energy, the sun. So obviously this is energy that comes directly from the sun in the form of light. It takes about 15 minutes for the Earth to receive enough energy from the sun to power the entire world for a year. If only we could harness all of that energy. So there's a couple of types of solar energy in APES that get confusing. So there's the active solar energy. It uses mechanical things, pumps, fans, storage. It uses equipment to actively capture the energy and so we can use it. So it's got a solar collector, and it uses fluids that circulate up as the sun heats those fluids and it turns it into energy. The other way is passive solar energy, and that's just letting the sun heat whatever it is up. So it doesn't use any equipment. It uses convection, warm rising, cold sinking to control how heat and cool things interact and flow. Back in the old-timey times, solar heating was used in our homes. Any home that was built before electricity would face south because you knew in the morning the sun would come up and warm the home, and then during the day it would get hotter and hotter and the sun would go behind and start cooling the home early. And so it was a form of passive heating for the home to be facing south. Now it doesn't matter which way we are facing because we have electricity or whatever it is we use to heat and cool our homes. Another thing we do is put a solar collector up on the roof, and sometimes we do this for water heating. You can see these like cloth things laid out on roofs, and it's a solar collector, and it heats up the material and it flows the heat down to this hot water tank, and that's where you get your hot water from. So that's another way to use solar energy for heating. That's different than when we use it for electricity. So electricity is this, the photovoltaic cell. That's when we take solar energy and we convert it into those moving electrons, which is electricity. The materials are made out of silicone and different metals that are able to conduct electricity. The panels then connect to the grid, and you can connect panels and daisy chain them together to generate more energy for the more people that live there. So what's happening, if you care about the physics/chemistry of this, electrons that move are electricity. That is the very definition of what electricity is, electrons that flow. And what happens is the sun sends photons, which are little packets of light, and it flows through these layers in the solar panel once the light reaches Earth, and then the photons will go in between these layers. You don't have to know about these layers unless you're going to take AP Physics. And then the layers make the electrons move. They get excited, the packets excite, and then the electron starts to move. Again, anytime an electron is moving, that is the definition of electricity. And so it goes along this panel, which is just a circuit, and the circuit moves along, can provide energy to turn on your computer, light your light bulb, and it just cycles about, and then whatever's extra will flow back to the grid. So normally a house is pulling off of these power lines and using all the energy, but when you have solar panels, you use all your energy, and whatever's left over actually goes back out to the power lines, and you get a little credit on your electric bill for making more electricity than you are using in your home. Now there's this curve people have been talking about lately called the duck curve. The duck curve says this: at night, there's no sun. We have this normal-ish amount of energy that's in demand at nighttime. When the sun comes up, we wake up, we start using electricity, but since the sun is up, we don't need this fossil fuel energy if we all have solar panels. So this fossil fuel demand goes down as the day begins, as we have sun. And so we are generating a lot more energy than we're using, so that's a good thing. We are lowering the demand on the system. But then when the sun goes down, we aren't making our solar energy anymore, and now we're demanding way more energy at night when we get home from work, turn all of our stuff on, and it stresses the grid out from going to not having to do anything all day to, whoa, we all need it now. And that's why we get rolling blackouts and power energy problems. So that's what the duck curve's kind of telling us. Okay, so solar's got some pros and some cons. It does not use or produce, a lot of carbon dioxide. There's a huge job market in it. Summer sales for solar panels are crazy money right now. There's a lot of potential for growth, and the sun is free, so that makes it kind of nice. They're not super efficient yet, but they are efficient enough that they're worthwhile to look into. But again, at night, when it's cloudy, when it's raining, what do you do if that's your only source of energy? It does use a bit of water. It can disrupt desert ecosystems if we're talking about a big solar farm, and pretty much expensive right now. We are getting some tax rebates. I think it's important to point out that there is rooftop solar, and then there's a solar farm. And the rooftop is just for your home, basically. It's enough to be self-sustainable for your electricity. These solar farms are like what was shown earlier, and you've got it out in the desert, and you've got this big array of solar panels, and that can affect these ecosystems. It can create some political problems and some other issues. So this is solar in a nutshell. Please read the handouts and make sure you know the difference between active and passive, and then understand that's more for heating. I can't write with this mouse, I'm sorry. And then the solar panels themselves, those are for electricity. So the rooftop solar or the solar farm, that's for electricity. So I hope that helps a little bit with the CED, but please explore more about solar as you have questions.